Have you ever tried pressing a syringe and noticed how the liquid squirts out evenly from the tip, no matter how softly you push? That simple moment holds the essence of one of the most powerful principles in fluid physics, Pascal's law. So, what exactly is Pascal's law? It states that pressure applied to an enclosed fluid is transmitted equally in all directions throughout the fluid. Let's break it down. Pressure, denoted by P, is calculated as force divided by area. That is, P equals F divided by A, where F is the applied force in newtons and A is the area in square meters. This means when we apply pressure to a confined fluid, like in a syringe or a hydraulic jack, that pressure doesn't just stay in one spot, it spreads out equally in all directions, affecting the entire system. This principle forms the backbone of many machines around us, from car brakes to heavy-lift hydraulic platforms. Let's explore how. Now imagine this, you apply a small force on a small piston, and like magic, a huge car lifts on the other end. That's not magic, it's Pascal's law in action. In hydraulic machines, we use two pistons, a small input piston and a large output piston, connected by fluid. Here's the key relationship, F1 over A1 equals F2 over A2. That is, F1 divided by A1 equals F2 divided by A2. Rearranging, we get F2 equals A2 divided by A1 times F1. This shows how a small force at the smaller piston creates a much larger force at the bigger piston thanks to the larger area. Think of a hydraulic lift in a garage. The mechanic pushes a lever gently and the lift raises the car, all because pressure travels equally and acts over a bigger area. Let's get behind the wheel, literally. Your car's brake system is a perfect example of Pascal's law at work. When you press the brake pedal, you apply force to brake fluid inside the master cylinder. That pressure travels undiminished through the fluid to all four brake pads. The result? Equal and simultaneous braking force on all wheels, smooth, safe, and effective. Even a small foot press creates enough pressure to stop a speeding car because the fluid transmits that pressure efficiently across the system. So next time you stop at a traffic signal, thank Pascal's law for doing the heavy lifting. Now let's broaden our view. Pascal's law isn't just for cars and syringes, it's everywhere in engineering. In hydraulic presses, immense pressure is used to mold, cut, or shape materials. Hydraulic jacks lift heavy vehicles with ease. Dental chairs move up and down with minimal effort. And giant earth movers use hydraulic arms to scoop and dig with immense power. All of these machines multiply small input forces into large output forces thanks to equal pressure transmission through fluids. It's efficient, powerful, and beautifully engineered. Let's now do a little number crunching to see how Pascal's law gives us that lifting power. Say, the small piston has an area of 0.01 square meters and a force of 200 newtons is applied. The larger piston has an area of 0.5 square meters. Using the formula F2 equals A2 divided by A1 times F1, we get F2 equals 0.5 divided by 0.01 times 200, which gives F2 equals 10,000 newtons. Yes, just 200 newtons at the input results in 10,000 newtons at the output. That's a 50 times increase. This is how hydraulic systems can lift trucks, move bridges, and crush metal with just a little push. Let's solve a practical question together. A hydraulic lift has a small piston of area 0.02 square meters and a larger piston of area 0.4 square meters. A force of 150 newtons is applied to the small piston. What's the force exerted by the larger piston? Start with Pascal's law, F1 over A1 equals F2 over A2. Substitute the values 150 divided by 0.02 equals F2 divided by 0.4, cross multiplying gives F2 equals 150 times 0.4 divided by 0.02, which equals 3000 newtons. So, by applying just 150 newtons, we get 3000 newtons on the output. That's Pascal's law, turning small input into mighty output. Let's quickly recap what we've discovered about Pascal's law. First, we saw that pressure applied to a fluid is transmitted equally in all directions. That's Pascal's principle. We learned that in hydraulic systems, F2 equals A2 divided by A2 times F1, and how a small force becomes a large one through area-based amplification. We looked at real-world applications, from hydraulic lifts and car brakes to earth movers and dentist chairs. Pascal's law is quietly working in the background, making modern engineering more powerful and efficient. I hope you now see how this elegant law makes the impossible seem effortless. Until next time, stay curious and keep questioning physics around you.